Okay, let's go. Let's go. First, I'd like to say that this is a strange talk. It's a kind of talk that I didn't know where to put it, in what event would fit. And since I know the organization of this conference, I decided to submit it here. Because it is a talk that it's designed for a very narrow audience. Because it's not only about complexity in distributed applications that run in parallel. It's also about applications that are developed by several people. Who here has had to manage a group of 5 developers, 6 developers? Okay, you've probably realized that managing 6 people is way more difficult than managing 6 servers. Okay? So this talk is about these kind of things. I mean, what happens when you have to manage a system that is both distributed, because it runs distributed, and because it's made by different people. And honestly, I expected a smaller audience. I usually give talks in conferences with almost empty rooms, because I like to talk about weird things. This is my Twitter. I don't spam too much. My PhD is on aerospace engineering. Yes, I did a PhD on weird stuff. Probably know more about theory of turbulence than I know about computing. And now I work at a company that also sponsors this event. And I have kind of a shared position with the Carlos III University. I usually say that I use Python because before it was cool. It doesn't have, I mean, it's not anything special, but I usually say that I use numeric. When I go to conferences, very few people have ever used numeric. And also used nuplot, which is not a particularly good thing. And I co-organized the first PyData in Spain, was held last year in Madrid. Come to me, we're hiring. And all the material of this talk is in this GitHub repo, including this article, which is kind of the point. I don't write books, but I like to write articles. And I think that are relevant. And there are no more slides, which is the kind of the point. We'll see that during the whole talk, I will try to make a point about how you must deal with complexity by communicating. First thing, let me introduce a small background about me. Again, I have a training I received a training as a scientist. I'm not a computer scientist. And during my PhD, I had to develop 2 kinds of applications. Ones that are short programs that were intended to eat some data, process it somehow, and then generate a result. Those were most of programs. But I also had to implement very large simulation codes that run in very large supercomputers. I'm talking about millions, of course, literally. Okay? And the curious thing was that both kind of programs, no matter if they used a server for a couple of hours or they used a supercomputer for 2 years, in both cases they had performance issues. So I had to take care of performance because, I mean, when you do a PhD, you cannot run out of time. You cannot spend 10 years doing your PhD, or basically you run your life. In both cases, I had performance issues. And in the case of large programs, and our programs that literally spend hundreds of millions of CPU time, in both cases, those codes were done by a single person and in a panic mode, constant panic mode. Okay? It's not a nice place to be. You develop for 1 year in constant panic mode, so you get older faster, which is basically what happens to you. But when I finished my PhD, I was approached by a company, and they told me, okay, we think that you know about computing, at least on a theoretical level. You know about high-performance computing. And they told me, we have several tools that may suffer from performance issues in the future, serious performance issues in the future. So we found an agreement, which is that I had 2 years to look what was going on, to understand what was the problem, to find the solution, and to implement it in Python. Really, Python was not a requirement, but I thought that Python could do a great job at that. I will expand also my argument on that. So this is the point. I mean, I had 2 years. That's a nice place to be. I have 2 years for researching. And again, this talk is about one topic that is not very much discussed, which is application architecture. And it is a domain that's strange. Because usually when you say, okay, I have this very large application, I want you that you're an application architect. That's what it says on your business card. You're an application architect. You get a lot of money by architecting applications, whatever that means. So what do you do? And usually when you ask an application architect, they always have the same answer, which is they tell you to repeat the same path that they took. This is a kind of path to success. I've been successful. You repeat that, and you will be successful too. And as I'm a scientist, this triggers me immediately. Because if you repeat something, you have no guarantee that it will be successful again. Otherwise, if you repeat a recipe for failure, you can be almost sure that you will fail again. Okay? So the problem was that I could not understand what were the company's problems. I couldn't understand what they were doing, so I decided to get my hands dirty and kind of do everything from scratch, okay? So again, this is the framework, big applications, years of development, tens of people, are applications that run maybe, the current design lasts for decades. And they do such things as assessing the whole risk of a complete bank. So we're not talking about this kind of script that you run for a month. So those things in which you have to take some time to learn about the architecture and doing it well. Okay, so how was the big way of solving that for 50 years? Have you ever heard of the entire architecture or the layer architecture? 3-layer architecture, which is that you have a layer of data, a layer of business, and a layer of presentation. And that's it. This is dead, completely. I mean, if you go with that story to anyone, they will tell you, I mean, they will basically fire you. Because that's something that people did 20 years ago. Now, no one does that. Now you do big applications. And I have a theory on why that thing died. Most people think that it died because of performance issues. Because you have a single pipeline, and you want to internet scale, then you need distributed stuff. Well, that's not a problem of architecture. What I think that it killed that simple architecture was complexity. Now you don't have a single database. You may have 3 different databases. Maybe I have a database right at the front end just for caching. Maybe you have 25 models for business. Maybe you have 3 different kind of clients. You have web clients, you have mobile clients. They need different things, or you offer different things. So this kind of blew up because of complexity, not because of performance issues. Performance also played a role, but I think that it wasn't the thing that killed it all. So now we have a reality, is that things are distributed. We have lots of components, and this is how applications are done now. We have a series of components, and we integrate them. For instance, if you want to support full-text search in your applications, what do you do? What did you do 10 years ago? You integrated a full-text search engine in your database, Lucene or whatever. Now people don't even remember what Lucene is. They just push the data to Elasticsearch, and you have full-text search. You want to visualize. You don't create your visualization layer. Probably your customer says, okay, I already have a Tableau license. Just use my Tableau. Who knows what Tableau is? So they're telling you that. Just integrate this component to me, or to your tool, because I'm already paying that. And there are several tools. I mean, I've just set a couple of examples. So again, this is about integrating tools. It is about, and of course, if you integrate you make your application from individual components that scale, you kind of wish that your application will scale. This is usually true, but it's wishful thinking. So this has a byproduct. So you have all the things scattered around, and you have to glue them somehow. And I knew, and I've been told many times, that Python is a great glue language. The problem is that you no longer need glue for gluing different libraries. You need glue for gluing components. And when I start asking about that, I got three kind of answers. Was use a message queue, or a broker like Kafka, or a message queue like ZeroMQ or RabbitMQ. I mean, there are a handful of them. Just use a kind of streaming library, okay? Or, so basically there were two answers. So a message queue or streaming library. But the problem when you want, or someone tells you to use a third-party tool is that you must know what you're about to do. Because you bet on a third-party tool that is basically yet another component. If that fits if you don't know enough about your problem and you choose a tool, and it happens 1 year after you begin coding that's not right enough, you're screwed, okay? So that was my problem. I didn't know enough about my problem to choose a glue. So I did my own. It's called, the whole project is called Palm, and my glue is called Pilm, P-Y-L-M. If you look at the document, you will find the link there. And it's something that was designed to scratch our own itch. And it's been successful. So it's one of the conclusions I will get at the end. I mean, building our own streaming library was possible and it was successful, okay? So again, you have components scattered all around, a glue that glues all the components together, but that has an important byproduct. It means that there's no such thing as a business layer. It's scattered all around again. Where's your business? Where's your computational logic? What's your 2 + 2 = 4? It's all around. And that it means that the development has to be distributed too, because there's no such thing as a huge library with all your logic. It doesn't make sense anymore. And about that, there's an important adage of theory. Who knows about Conway's law? No one else. Conway's law is something that it's told to you when you start developing in large teams. There's a short way of explaining Conway's law, is that if you have 5 people, there will be 4 modules because one has to lead, okay? By the way, this is not mine. This phrase is by the late Peter Hitchens, who gave great talks about this kind of things and distributed systems. It means that what Conway's law says is you cannot decouple the social structure that you use for coding, the people, from the product they make, which is the code. And usually it was used as a sign of warning, is that if you don't improve the communication between the developers, you will have a decoupled software. Okay, what we've realized after 2 years is that you have to embrace that. 1 model per developer, that's fine. That has one caveat, which is that you have to be very good at packaging, and you need a kind of a bookkeeper who knows which model does what, so you don't throw away code. But it has a very important thing, is that if you let someone write a single module, then they have a sense of responsibility and liability. If something goes wrong, it's their module. They know what happened, and they feel responsible for everything working, which is a good thing. And, but again, that's kind of a guideline of what things to do. And then you go to application design. This is all very abstract. Do this, do that, you can try to do this, you can try to do that. From the scientist's point of view, I know that you cannot tell when you're right, but you can know when you are wrong. Okay, as I'm an aerospace engineer, I know that there are other design disciplines other than Agile and Waterfall and all the things that are fashionable now. There's one I particularly like, which is axiomatic design. Probably none of you have ever heard of axiomatic design, don't you? It's a very hidden practice of mechanical engineering. Axiomatic design, which worked, that's why Japanese are very good at engineering. It's a Japanese thing. It says is that you can more or less judge your designs, no matter what you're designing, by 2 axioms. You have the maximum independence axiom and minimum information axiom. It means that if you have a series of functional requirements, whatever they are, components, your good design is not bad if those components are very independent from each other. This is the independence axiom. And the information axiom is that you should need the lowest amount of information to describe those components. This is the minimum information axiom. If you think about that, they're mutually exclusive. It means that if you try to be very precise, okay, you need a lot of information to define your system. And if you want to be very brief, then you're ambiguous. So that's hard. There's no maximum. That's no obvious maximum on that. Okay? So now we're kind of set our ground where we can start more or less developing what we know. Okay? We have a criterion to know if we're going wrong, if we're doing things wrong. And we know that we have those big applications built with components scattered all around, and we have to glue them somehow. Okay? Now we have a huge problem of complexity, a big one, because everything's scattered around, and we have a group of people working separately. So how we deal with complexity. And the thing is that this is kind of trivial. We only have one way of dealing with complexity that we know, and it works, which is abstraction. There's only one, I think. Maybe there's a philosopher that says that there's a different one. But I only know about one, which is abstraction. If you think about computing, computing is built with abstractions over abstractions. Python is a huge abstraction. You have pandas that is built on top of NumPy, that's built on top of Python, that's an interpreter coded in C, that has a virtual machine that translates to bytecode until ones and zeros in one piece of silicon. It's abstraction over abstraction. So new applications are yet another abstraction. So we have components and glue. So we have to design better abstractions to understand that. Okay? And again, remember that we have this whole thing of the axiomatic design that is a kind of guideline. So if we build very good abstractions that are orthogonal or independent, they're good abstractions. Okay? That's the independence axiom. If we don't need so much information to define them, then they're good abstractions because of the information axiom. So again, good abstractions are the ones that they build a set that is independent from one from each other, and at the same time, one single abstraction has a lot of meaning. And I will try to exemplify that. So how to make good abstractions? Or how to make smart abstractions. I think that there's only one way of doing that, which is talking to smart people. This is how we become smarter, talking to smarter people. And when the first time I said that, someone asked me, okay, how do you do if you don't know any very smart people? I always say, okay, a friend will do. Just pick a friend or a coworker. And then what happens after that is okay, what happens if I don't have any friends? And there's a solution for that too. One of the most important and fruitful experiences we had is discussing abstractions. Setting up a meeting, going to a whiteboard, and discussing an abstraction. There's one particular thing about this kind of building abstractions and organizing what you're doing. It is that abstractions never get bike-shedded because they're hard. In 2 years, I've never had an unfruitful conversation about abstractions. And let me put some examples on that. Oh, by the way, the thing for which I think that groups don't discuss abstractions so much is because they're hard, and people get them wrong all the time. So it's very possible that you get a meeting on your abstractions, and once you've designed, and you get burned. Someone tells you that's not good enough. So that's the kind of attitude that blocks that. Not discussing, the fear of getting wrong, or someone tells you that the thing that you've done is not good enough. My advice for that is that if you're wrong, you will have to correct it anyways. So the sooner or better. I have an example for that. The Palm project, again, the glue, which is Palm, is just a part of the Palm project, has a functional part, which is evaluating things that have to do with a risk of a bank, for instance, mortgages. I don't know if you know, but there are like 100 different kinds of mortgages. Bullet, French, German, with prepayment, without prepayment. Some are stratified. You have problems with scheduling. So you can imagine that that's a problem of complexity too. How you model all those mortgages. And one of our most senior developers did that. We set up a meeting, and our conclusion was that it was not good enough. And we threw that away. Then we tried again. And then one engineer picked the development and said, oh, every time that I have to change the code of a mortgage, I have to change 3 different classes, 2 different files. That is not good enough. And what that engineer did was exactly what any engineer should do. She didn't know what to do, so she immediately set up a meeting. And again, with what she learned already, she discussed the abstractions with everyone. And now we have a module that kind of works, or at least for some time, until we find that those abstractions are not good enough. And this is the only way. So again, what happens if you don't have any friends? Which is a kind of a hard thing. Then there's only one way, which is writing good documentation. It's not that hard. You only have to explain things to yourself. Doc strings are not good enough. That's the big phrase. If you only do doc strings, you're doing documentation wrong. And I think that's one of the mistakes of how the Java development was done at my company. So you have to explain things to yourself, and that's something that happened to me. When I was building this glue, this thing called PILM, we had a first version that had some hypotheses. And it was nice. From the engineering point of view, it was nice. I mean, you had components that were very similar. So schedulers were similar than workers, and they kind of self-organize. And there was a fail tolerance built in them. But what happened was that it was so hard to use. Then one engineer picked up, and I saw that it was struggling. There was something that it wasn't working in the abstractions. I mean, how you actually had to use the library, and that's bad. But and then we also had problems with the GIL. Sometimes the components freeze, but that is fixable. How I really realized that I had to throw away 3 months' worth of code is that when I started writing documentation, I realized that all that was bullshit. So I took what I learned, I threw away 3 months of work, and started over. And it was the only way. Okay? I'm not missing anything? Oh, yeah. This has a collateral thing. If you cannot discuss things with anyone, just don't put it in your code. Don't do it. It's over-engineering. It's the first step to over-engineering. No one asked you for that. You're putting anyways. Probably it will be wrong. So don't do it. This is what happened with the whole fail tolerance thing I put on the first library. It happened that my company didn't need fail tolerance because 99.999% of errors are user input. So why putting that? It's just rubbish, something that makes the maintenance more complex. So I also removed that. The second version didn't have any kind of fail tolerance because no one needed it. That's it. So again, with this practice, writing good documentation, having those meetings discussing abstractions, you get better and better. Again, you make better abstractions just how you get smarter, just communicating and practicing. And there's a symptom in which you really get, and this is it's very difficult to explain, you just get it, that you're getting better and better at abstractions. It's just that when they just emerge naturally. What happened is that when I was developing the second version of the glue, the PILM thing, the PILM library, what I realized what I was developing is that while I was developing, everything was getting very complicated. And I realized that I needed 2 levels of abstraction. One level of abstraction that was kind of the ground that I was doing abstractions such as routers, connections, message queues, components, servers. Something that I needed myself to develop that was something quite complicated. But of course, that API, that abstraction, was not good enough for a user because that's too complicated. That's low level. So I built a second abstraction layer on top of that. That's the one that a normal person should use. So this kind of things that, I built a 2-level abstraction layer. It's kind of, okay, I'm getting decent at that. Not good because, of course, I had to change things, lots of things. But it's kind of, okay, I'm getting into this. Another important thing about abstractions, you have everything that's distributed. So don't get too much centered on components. Those components have to communicate somehow. And you need to design how those components communicate. So that is also a great chance of designing good abstractions, because you have one guy talking to another guy. Maybe one of the most successful ideas we had during those 2 years is one thing called IDN. IDN is a language in which the front end communicates to the back end. IDN is one thing that we use to describe complete portfolios of financial institutions, and it is a language. That's very easy to parse. It also comes with a small interpreter and a small virtual machine, but it's a language. So that's kind of the ultimate abstraction, a language. And what it happened to me, and it's something that surprised me, is that that was not that hard. Languages and this kind of abstractions that seem crazy, they're not that hard to do. So I encourage that if you have two things that have a hard time communicating with trivial types like ints or strings or whatever, you try to design an abstraction that makes sense. Now we have two components in which the one component says to another component, this is a portfolio, which is nice. So again, this is more or less what we have. We get better at designing abstractions. But the problem is that those abstractions are not, most of them are not future-proof. Because again, it's about communicating. What happens when people leave or switch departments? Or it's not, they had 100% dedication on that project, and then they move them to a different project. What happens then? And there are different ways in which we have to deal with those things. The first one is, again, writing good documentation. But what is good documentation? What really builds a team when you're building something, when you have someone very close or by your desk, you don't only tell him or tell her how that thing works or how you must call a function. You usually tell him or her, I did that because I wanted that. That was my intention. This is what I pursued. So you want some empathy. It's like, that's not arbitrary. This has a reason. So writing good documentation, and I think that Python is better at that, documentation must read like a book. That's important. That's what I said. One of the big things here is doc strings are not enough. It should read like a book. And this book should not only have how to use it, it should have also what you want, the reason why you did things that way. Because that gives extra information for the person that's reading what you did. Say, okay, now I get it. This is right, this is wrong. Because that was his or her intention. Okay? So good documentation. The other important thing is that I said that we wanted to make our own library, our own glue. And that turned out to be successful. Because we kind of handled the early risks. If you build something yourself, you have the risk of not being successful and having to throw everything away. But that's a short-term risk. You may be successful or not. The problem is that when you use a third-party tool, you have a long-term risk. Maybe that was not the right choice. Maybe you find a bug. Maybe you need a hack and you know how to do it. And what happened is that when we really realized that the Pilm thing was successful for us is when we started wanting to hack it to get more features. It was our code. It was our library, so we could do it. We knew 100% of lines of code of that. So we could do it. And that's great. It means that if we need a hack, we can even turn it into a feature, which is good. So again, documentation, not being afraid of doing things yourself. And again, as I said, you need a bookkeeper. You need someone that more or less knows where everything is, because distributed things get very, very complicated. It gets scattered all around. okay? But if you really want to get a conclusion from this talk, and I think that that conclusion is important if you start managing or working with a lot of people, it's getting better at communicating. Again, it's the only trick, okay? It's always said that the good meetings or the good conclusions are the ones you get after 10 minutes in a whiteboard. And I'm really trying to tell you that you must go beyond that. I mean, you should do it without the whiteboard. That's all I have. I'm sorry it was too abstract, but it was kind of the point.
Hello. I have a question regarding documentation, because at least one of the problems we have in all the works I've done is that it's very easy to write a first version of the documentation of what you want to achieve, but what is really hard is to keep this updated when things change, and if you have a very complex environment with multiple components, it's even harder. So how do you used to manage in your work, how to, I don't know, keep this documentation updated in a way it's easy to do, and you don't have to constantly, for every change you do, check the documentation to see if you are breaking the vision or whatever?
Mm-hmm. One of the things that it was one of the management's idea is that we have our documentation in our continuous integration system. And there are some engineers that don't read the documentation from the package, but from the continuous integration system. And if they find that something is not well documented, they complain immediately. So I've realized that the thing that motivates you to change documentation is someone complaining. So we kind of encourage that thing. It's like, no, here's the documentation, don't ask me. Read the documentation, there's something wrong, complain. Then we have a motivation to understand that documentation is important, also for communication.
You made an interesting comment about the Conway's Law and the team of 5 people and having different modules and ownership of those modules by different people. I sometimes encounter that it's when people think of code as their code, that as opposed to someone else's, and that relationship can sometimes make it so people don't help out on other people's code because it's not theirs. It's this, oh, I'm not going to touch that code. It's that person's code. Mm-hmm. Do you have any techniques to try to encourage people to, if they find a problem in someone else's code, to at least help with that, or to encourage not siloing people off in that regard?
This happened by the way, this happened by mere luck, which is that we found that the module improved so much when the original developer moved to a different project. So that module was not his anymore. Someone picked the development up, and it works so well. So it's something that I'd say that maybe is a nice practice, is that don't let anyone code a single module for more than 1 year. Move it to a different thing and pick another guy that just reviews that, sits down with the original developer for 1 week. Sometimes you need less than that, explains that module, and then picks up the development. So the sense of ownership is also a temporary thing. I don't agree that anyone must develop any code for more than 2 years. That's not healthy.
Hello, thanks for the talk. Regarding this topic, in that particular case, don't you fear the feeling of the new developer to recode the component? Happened to me, that's why I'm asking.
What happens is that usually you have kind of a godfather, someone that, in this case, is kind of me, someone that sits down with the 2 developers and said, okay, don't hash everything, don't destroy everything. Try to be constructive, because that thing was coded by a human being, so you must be polite. It's curious because that's, I think that's I mean, basically you act as a maintainer. The same kind of someone's in an open source project wants a new feature, usually the maintainer says, look at all the code. Probably there's something that you can reuse. Don't just add lines of code because you want to do it. So someone has to act as a kind of maintainer, and a referee between those two engineers. And what it naturally happens is that, and this is important, usually the abstractions change, they get better, and you reuse code. That's what happened, for instance, with the mortgage thing. Most of the logic was recycled, but the abstractions changed completely. So we had the same functionality with better abstractions. That's the kind of thing you should encourage with that. Oh, by the way, there's something I missed. That's the problem of not having slides. If you realize, most successful open source projects kind of use this. And you realize that when you submit a pull request, usually the discussion, it's not only about code, but about the intentions, about the abstractions. That discussion also gets there. And about the communication, it's good. I mean, the good communities have also codes of conduct to encourage the fact that communication is also fruitful.
I think that's it. Let's thank Guillem again.